Welcome everyone. Today we will be discussing input and input-output equation in system dynamics. This equation describes how the output of a system depends on input, usually through differential equation in time domain. The capture of external behavior of a system. How the system reacts to external stimuli without explicitly modeling the internal states, such as velocity, current, or temperature. What are input and output equations? An input-output equation is a mathematical relationship that links the input to the output. It simplifies the analysis by focusing only on what we can measure, the input signal and the output response. Think of it as a black box model of the system. We don't necessarily care about the internal details, only about how the input affects the output. Why do we use the input-output equation? We use input-output equation because they simplify analysis by focusing on measurable quantities. And second, provide a black box view of system behavior. The third, from the foundation for deriving transfer functions, which are critical for analyzing system responses and designing controllers. In short, input and input-output equations are our first step in moving from the physical system to a mathematical model. The characteristic of input-output equations include they are generally expressed as differential equations. They link the input variables directly to the output variables. They might eliminate internal states or hidden variables. This means we get a clear relationship between what we put into the system and what we observe coming out. How to derive input and output equations? The process of deriving input-output equation usually follow these steps. First, model the system using physical principles such as Newton's law, or Kirchhoff's law. And then write down the differential equations governing the systems. Third, identify the output and output variables. And then eliminate any internal states such as current, angular velocity, or intermediate displacements. And then finally, rearrange everything to express the output solely in terms of the input. In general, an input and output equations look like this. We have general differential equation connecting input and output here. So we have y here is output, and then u function of t is input. So if we get input here, we get the result from these equations. Here the input is the applied force for where y function of t is the output and u function of t is the input. This compact form is the foundation of transfer function. So this one is only general, not necessarily always like this. Okay. For example, we apply we apply Newton's second law to a mass spring damper system like this. We have external force here, and there is Hooke's law from the spring, and we have here the damper. And we have here mass M, the damper coefficient B here, and stiffness of the spring K, and we have external force. We can write the differential equation for this, or equation of motion of this mass, like this. Here the input is applied force. Input is applied force F, function of time, and the output is the displacement or position of the mass. This already an input output equations. Okay. What is a transfer function? Now let's move from the time domain to the frequency domain. The transfer function is a mathematical tool that relates the output of a system to its input. But in the Laplace domain, it transforms complicated differential equations into much simpler algebraic equations. So here we have transfer function G, function of S is in domain, frequency domain, and we know here that transfer function is ratio of the Laplace transform of the output to the input, assuming zero initial conditions. So this is the output, and this is the input. Laplace transform of the output, Y, this, and Laplace transform of the input. Yeah. So we have input. Here we have input and transfer function connecting between input and output. Okay. Transfer functions are important because they convert differential equation into algebraic equations, make system analysis and design much easier, especially in control engineering. Provide insight into system properties like stability, response, speed, oscillation, and damping. Allow us to stimulate and predict system behavior in both time and frequency domains. So transfer function are a key tool in engineering, in control engineering. In general, the transfer function has the form like this. In general, this no, I mean this is a general form of input and output equation, right? Not general. For example, we have input and output the equation time domain for that mass M for this case, I mean. For example, mass spring damper system. Okay. We apply Laplace transform for left side and right side, I mean, for both sides. So we have From left side, we have like this, Laplace transform. And from the right side, we have this one. We assume zero initial condition, of course. Zero initial conditions. We can collect this one. I mean factor. We can rewrite like this, and this is the transfer function. So connecting between output, this is the output and input, right? Laplace transform of the output and input. For example, transfer function like this, first order systems, we have time response exponential decay for this one. How can we know this one is exponential decay? We can find the inverse of Laplace transform if we want to know that this is exponential decay. And the pole as equal -2 stable. I mean, it will decay, not if we impute s equal to -2, we have the transfer function is infinite, right? And other example, second order system like this. And this is omega n is natural frequency, zeta is damping ratio. This is for uh, mass spring system actually. And this is general form of transfer functions. We have numerator 0, determine the frequency where the output is 0, and denominator false, determine system dynamics and stability. System order, highest power of S is in the denominator. If we have like this impulse, the Laplace form is 1. This is natural response core behavior. Laplace transform of impulse is 1. And if we have step function, the Laplace transform is like this. This is steady state performance. Or we have RAM. If we do Laplace transform of RAM, we have like this. This is measured steady state error. And sinusoidal, we can get Laplace form like this. This is frequency behavior. So this is poles and zero physical interpretations. If we have location of poles, if we have pole in negative real axis, it means stable decaying response. But if the poles in positive real axis, I mean, we have unstable behavior. If the location of pole is complex conjugates, this oscillatory behavior, and if it's in imaginary axis only, then sustained oscillation. This is the physical interpretation of poles and zero. So dynamic system modeling, okay. So we have already learned about transfer function, how Laplace transform uh, useful for transfer function here. So transfer function simplify our analysis here. Thank you very much for your attention. See you.